Hello, good evening, everyone, and welcome to the ENLIGHT lecture series. My name is Anna Savitske. I'm an ENLIGHT project coordinator at the University of Göttingen, and today I have the pleasure of moderating this lecture with a focus on the future of energy. I'm delighted to introduce to you our four presenters today. Luka Tas from the University of Ghent in Belgium, who is joined by your colleague Zhang from the University of Ghent as well. Our third presenter today is Professor Rory Monaghan from the University of Galway. And last but not least, Ana Picayo Perez from the University of the Basque Country, north of Spain. We will proceed in this order today. So I will begin by introducing our first speaker, Luka Tas from the University of Ghent, who will give a talk on the future of aquifer thermal energy storage systems targeting complex aquifers and informed decision making. We will begin with this first talk and move on with the rest of the talks before proceeding with the discussion. So each speaker has about 10 minutes to present their topic, and then we'll have time to address your questions for a discussion at the end. So if you're a viewer joining us today, you won't be able to turn on your microphone or your camera, but you can post your questions to each of the presenters in the chat. We'll make sure to gather them and address them at the end. So we'll begin with the first speaker. Luka is a strong advocate of the use of aquifer thermal energy storage systems to achieve sustainable development. Shallow thermal energy storage is a well-known concept, but its use in many countries remains the exception rather than the rule, even in times of energy and climate crisis. She is convinced that there is still a strong need to have a methodology that can be applied in practice for optimization of these ATES systems and for risk assessment of the decision involved. Her current research as a PhD student at the University of Ghent, funded by FWO, focuses on optimizing thermal energy storage in shallow aquifers through advanced uncertainty quantifications. And I'll pass on the microphone to you, Luka, and the floor is yours.
All right. Thank you, Anna, for introducing me. Can you see my screen?
Yes.
All right. So my name is Luka Tas, and today I want to introduce you to aquifer thermal energy storage systems and its future development. So first of all, we need to make sure that we're all on the same page of what ATES or aquifer thermal energy storage actually is. ATES can provide heating and cooling to buildings and in a green and sustainable way. And when you look at the pie charts over here, you can see that the building sector is responsible for about 40% of the global greenhouse gas emissions, of which 80% is used for heating and hot water production. And as you may know, also the demand for cooling is currently increasing. And when you look at it in this way, you can see that there's a strong saving potential if this thermal energy could be provided in a green way with ATES. But how can ATES provide heating and cooling to buildings? Well, ATES actually uses the thermal energy of the groundwater that's present in the shallow subsurface. And with shallow, I mean up to about 200 meters depth. At this depth, the average groundwater temperature is about 10 to 12 degrees, and this is clearly not enough to heat a building. So with ATES, there's still something else at play. ATES actually stores the thermal energy of the environment in the subsurface in order to use it when it's actually needed. To illustrate this, here you are looking at an ATES system in summer season, and in summer it's often too warm inside a building. So you extract water from the ground, and this water moves to the heat exchanger in the building. The water takes the heat from the inside environment, so the water warms up and the building will cool down. And this warmed up water is injected back into the groundwater reservoir, where you will create a zone of warmer water. In winter, the system is reversed to provide heating. So there you extract water from the warmer zone. So you take advantage of the previously stored heat, and this water moves again to the heat exchanger. So it gives its heat to the environment. So the building warms up and the water cools down again. And this cooled down water is injected back into the aquifer, where you will create a colder zone that can then be used for cooling in summer again. And as you can see, the temperature of the warm storage area is still only about 18 degrees Celsius, and this is still not enough to heat a building. So there's also a heat pump in the system to further increase the temperature of the groundwater. With ATES, you can, on average, save about half a kilogram of CO2 per pumped cubic meter of water. And also the power that you can generate with ATES is directly proportional to the flow rate of the system, so the amount of water that you extract and inject, and also the temperature difference that you create in the subsurface. And so in general, for ATES, it is sufficient to have a groundwater reservoir or aquifer in which you can pump or inject with a sufficiently high flow rate. And this immediately explains the very wide applicability of ATES systems, and also its great potential to mitigate CO2 emissions related to heating and cooling of buildings. If you want to implement an ATES system in practice, it should always be first preceded by a feasibility study. And the first thing that you need to know is, of course, the energy demand of the building that needs to be fulfilled by ATES. And second, it is very important to take into account that you store groundwater at a certain temperature in the subsurface, but you will not be able to recover all of this thermal energy again. This is because there is groundwater flow and conduction, for example, that cause the heat and cold to move away from the storage sites. And therefore, it's very important to know the groundwater flow and groundwater transport processes in the aquifer very well. And this is why often during a feasibility study, a three-dimensional model is created. And this model actually is a representation of the study site with its hydrogeological and thermal transport parameters. And this model can then serve to simulate an ATES system for the desired length of time, and then you can predict the temperature evolution with time. And with this prediction, you can also calculate the expected power output of the ATES system and also the thermal recovery efficiency. Despite the apparent simplicity of making such a model, it's a very challenging and also a time-consuming task to make models that actually make reliable and realistic predictions, and there are also many uncertainties involved. Despite these challenges, there are already many operational ATES systems in the world. And so for the interpretation of the results, you can often also rely on experience. Most of the operational ATES systems are located in thick productive aquifer layers because these are the most promising areas. And this immediately also explains its prevalence in the Netherlands, which is typically characterized by this kind of aquifers. However, in many other European countries, there are more complex aquifers which are more at the limit of suitability for ATES. And because the potential for ATES has already been extensively proven, and as we're still facing challenges to provide our energy in a green and sustainable way, there is currently a tendency to also target these more complex aquifers for ATES. And this is also aided by government incentives to invest in green energy and also by the rising energy cost, which favors the investment in ATES systems. Because there are coming more and more ATES systems, this brings its own challenges for the future. First of all, I want to talk about competition between systems. When you have more and more systems in a certain area, they could be placed too close to each other, and this might cause some interactions between individual ATES systems. And this is potentially detrimental to the efficiency of each system. And this is something that's actually already encountered in the Netherlands. So in the future, it's very important to take this into account and to develop some kind of legislation so that we can actually optimize spacing between individual ATES systems to avoid this competition and also encourage district heating plans. If you want to target more complex aquifers in the future that are at the limit of suitability for ATES, you need to take into account that there the risk of failure is significantly higher. And then it's not enough anymore to rely on experience when you design the system, but better informed predictions should be made. However, the current methods in industry have poor predictive capacities and are unable to estimate this uncertainty. In practice, often a field test is carried out, and you try to fit your model output with this field test, and you do this by adjusting your model parameters. And this is called a deterministic calibration. However, there are some issues with this approach because it does not take into account that the field test is only representative for a small part of the study area. And it also does not take into account that actually multiple model realizations with different parameter distributions could actually fit this field data. So to be able to move towards models in the future which can serve for real risk assessment, we need to develop methods that can have better predictions, while also acknowledging uncertainties that are present. And at the basis of these new methods will probably be stochastic approaches, where you explore the entire ensemble of different of different solutions. To illustrate this, here you're looking at the model output that is a temperature evolution with time for 2 cycles of an A-test system. And you can see that there are many possible solutions. And this is because I included uncertainty by determining for each parameter a range in between which I think that the actual value should be located. And then I sampled different model realizations from these ranges and I generated the output. And now you can see that there are indeed many possible solutions instead of just one. And with further statistical data analysis, you can then make more accurate long-term predictions, also taking account the short-term field data, while still having an idea of the uncertainty that is present. And finally, I want to talk about the increasing complexity of data and models that is expected in the future. As I mentioned, there are already many operational ATAS systems in the world, and a lot of them have a lot of monitoring data that is available. And the challenge in the future lies in how to use all of this data to optimize future new ATAS systems in order to reduce the cost of the initial feasibility study of new ATAS systems so that we can promote the further use of ATAS in the future. Also, if we want to use more stochastic approaches in the future, this will also increase the complexity of models and data. And I expect that also the methodology with which we solve prediction problems in earth sciences will evolve along with this in the future. So to end this presentation, I would like to emphasize that decision-making should always be based on sound scientific approaches, and that as our research about ATAS systems advances, into account that there's still a gap between science and practice that we should try to bridge in order to actually make a real difference in practice. Here are still the references. So thank you for this presentation and for your attention.
Thank you very much, Luka, for your presentation. It's very interesting, and I'm pretty sure there will be a lot of questions during the discussion later. Thank you. But now we are moving on to Zhang, your fellow PhD candidate from the Department of Geology at Ghent University, with a talk on how to safely and efficiently extract geothermal energy in deep mines. His research focuses on deep geothermal energy and more specifically seeks to improve the thermohydromechanical modeling to reduce the uncertainties in the deep geothermal system predictions. His research project is mechanisms of rock mass and stability and co-mining of deep mineral and geothermal energy considering spatio-temporal distribution of stress and temperature, and this project is also funded by the FWO. And I'll pass on the microphone to Le. You can start with your talk.
Thanks for the introduction, and I'm going to share my screen. Now, can you see my screen?
Yes,
right.
Thank you.
All right, great. Hello, everyone. I'm Le from the Department of Geology at Ghent University. I'm delighted to be here today at the ENLIGHT EU lecture on the topic of the future of energy. I will be sharing some information about the deep geothermal energy and a project like how to safely and efficiently extract the geothermal energy in deep mine. Generally, the geothermal energy can be categorized into shallow geothermal and deep geothermal. And deep geothermal includes the deep hydrothermal resources and also ultra deep geothermal, such as hot geostroke resources. As shown in this figure, you can see two very significant characteristics of the deep geothermal. They are deeper and with a higher temperature. These two types of deep geothermal differs a lot. Between the hot dry rock resources with the hydrothermal resources, mainly due to the underground water, because the heat transfer medium is usually water in the geothermal system. So the hydrothermal have naturally high temperature reservoirs. It makes it easier to extract the hot water and re-inject the cold water there. However, for the hot georock, there is no water reservoir and often no fractures available for the water movement. Therefore, we need to create a pathway for water in the deep. This is achieved by the injection high pressure water into the rock. It will promote the fracture and also the development of a water circulation network. This system is commonly referred to as enhanced geothermal system. That's why we call it enhanced. The table provides here is a comparison between these two methods of deep geothermal. And in the underground and in the deep geothermal, we need to consider the complex physical environment of the reservoir. We all know the deeper, the higher the temperature, also the higher the pressure and stress. The injection of the cold water during the geothermal extraction, it will always disrupt the original physics balance environment, and normally it can increase the potential risks. And in the deep geothermal, the temperature, pressure, and stress and that environment, they are always interconnected. We call it the thermal hydromechanical coupled effect. And the risk always comes from the mechanical response of the reservoir. Normally, both the decrease of temperature and an increase in the pore pressure can reduce the effective stress within the reservoir. In rock mechanics, we use a Morse code to represent it. If the stress in the reservoir shifts but does not reach the yield surface, then it can be considered as safe. However, if the stress exceeds the yield surface, especially in some presence of faults, if there were some faults there, it can lead to a very big risk. So what's a very big risk? The answer is earthquake. 7 years ago in Pohang, South Korea, a 5.5 magnitude earthquake occurred. It's the largest and the most destructive earthquake ever associated with an enhanced geothermal system. This event it led to the complete shutdown of the EGS project there, and it was considered as a potential game changer for the global geothermal industry. Now we have enough information about the deep geothermal, especially the risks. Now I'm going to move forward, and I would like to introduce a new concept. How can we extract geothermal energy in deep mines? In theory, extracting the energy in deep mines, especially the geothermal system, is beneath the existing mining system. It can be a mutual benefit situation. On one hand, the geological data from the existing mines can be a reference for the geothermal, and the shaft, the tunnel, can reduce the cost of geothermal streaming. And on the other hand, the injection cold water, it can help to cool down the mining areas, controlling the heat hazard. So for this conceptual system, our primary concern is still remains the safety and stability of the system. as we previously discussed, safety is always a fundamental requirement of a system. So given that normally the deep mire environments are often 1 kilometers on the ground. So in this system, we are dealing with hydrothermal resources. We don't think about the hot jaw rocks thing. So there is the likelihood of the induced earthquake is nearly zero, but we cannot ignore the impact of the mechanical response from the geothermal to the stability of the mine gallery. So if we want to design this conceptual system, we have to pay a lot of attention to the stability of the mine gallery, also the temperature of the gallery to check the cooling effect and also the production temperature. Then the next question is, how can we connect the reality with the conceptual? We can employ the most commonly used method in geothermal research, the numerical modeling. A successful numerical modeling is like a calculator. You provide the model with the information you have, which include a lot of parameters. In this model, it should include the thermal parameter, hydraulic parameter, mechanical parameter, and the design parameter. There is a lot. And in return, the model will provide you with the answer you want. So which include the gallery stability, the gallery temperature, but also the production temperature about the project. It's quite a straightforward method. But in reality, we want to use a model to give a suggestion for decision making, such as we determining the the location and depth of our geothermal system, where and how deep we can make a best decision to build a geothermal system. We always have to face a big challenge. It's still the uncertainty. In numerical modeling, we deal with a lot of input parameters, each with a range of value that can influence the responses. The key question is how to select the most appropriate parameters range to make an accurate decision and achieve the desired results. This is our primary concern. Therefore, I'm going to introduce a simple approach to addressing this question and making the best decision. Instead of relying on just a single one model, we increase the number of models to X. X could be hundreds or thousands, it depends. Within the range of possible value for each parameter, we can select X sets of different model input. Then we run the model X times for the stochastic simulation. We generate a large number of responses. Among these responses, some gallery they may remain in a very stable situation. However, others may experience damage, and some production wells may achieve very ideal temperature, and others may work not very well. So based on the responses, we cluster and we do some classification and cluster the models to identify which parameter can result in the ideal responses. Then these parameters can be considered as a good value. It will help us to define the optimal design, provide the valuable guidance for decision making. And of course, this approach is quite straightforward, simple, but it will cost it's computationally intensive. We also employ some machine learning method to optimize deep geothermal model in a faster and simpler way. And if you are interested in the method I'm doing now, please feel free to contact me by the email. Thank you very much for your attention.
Thank you very much for your talk, for your very insightful talk, and a gentle reminder to the viewers to either keep your questions till the end for the discussion or post them in the chat right away, because now we are moving on to the third talk of today's lecture by Rory Monaghan, titled, "What Role Can Green Hydrogen Play in a Fully Decarbonized Energy System?" Rory is the professor in energy systems engineering at the University of Galway in Ireland. He is a funded investigator in Moray, Ireland's National Centre for Energy, Climate and Marine Research, and the lead investigator of the Energy Research Centre in the university's Ryan Institute. Rory's team works on several aspects of hydrogen supply chain research, including the EU-funded GenCon and Green Highland projects. He is the head of mechanical engineering and director of energy systems engineering program at the University of Galway. Rory is the coordinator of Shamrock, a project funded by the EU's Clean Hydrogen Partnership to build Ireland's first hydrogen valley. And now we have the pleasure of hearing his talk. The floor is yours, Rory.
Thank you very much for that introduction, Anna, and welcome to everyone. You can hopefully see my screen. So I'm going to speak for about 10 minutes about the role that green hydrogen could potentially play in getting ourselves off fossil fuels and getting ourselves to a zero emissions energy future. So first of all, to set some background, and you know, all of the talks that we've seen so far today, we've all been focused on similar issues. We're all interested in reducing fossil fuel exposure. We're all interested in reducing greenhouse gas emissions. And just by way to emphasize what's happening, we have a number of challenges that we need to face up to in Ireland and in Europe. And I'm obviously speaking from an Irish perspective, but everything that I'm saying here applies equally to Europe. We're all behind on meeting our emissions targets. We are all trying to deal with issues around the security of energy supply. These graphs show the quantity of the energy used in Ireland and Europe that is from imported energy. We've got some projections there for Ireland for how it might continue into the future. So we are very, very exposed in Europe, but we are extremely exposed in Ireland because we have traditionally virtually no fossil fuel resources. And then we have issues over the last couple of years on the physical security of supply that we faced, that we have growing energy demand, we have relatively stagnant energy supply in most European countries. In some countries, we have falling energy supply. So how can we aim to address all of these issues that really are very important issues for society and for the economy as well? Well, the first and most important and cheapest route to decarbonizing our energy system is simply to use less energy. This is a Sankey diagram showing the flow of energy from raw materials on the left-hand side to end uses on the right. The problem with these end uses is that this energy that's flowing into these different end uses in our economy, most of this is wasted. The majority of energy used for transportation is wasted because combustion of fuel in cars is an inefficient process. We can say similarly for houses, for industry, for other types of energy use. So if we can improve the efficiency of energy use on the right-hand side of this graph, we have to bring in less energy resources on the left. So efficiency, demand management, these are the first things we should be looking at. There needs to be an enormous change in how society thinks about energy, and how we get around, and how we use energy on our homes. There's, you know, this is a standard scene across Europe. You know, in the morning and afternoon, we have too much use of cars. We have too much use of cars that are used primarily by individuals. So there needs to be a large change in how society thinks about energy, thinks about emissions, and thinks about fuels. We need widespread electrification of as much as we can, as quick as we can. The two obvious routes for electrification are electrification of home heating and cooling through the use of heat pumps, and the electrification of small-scale transportation through the use of electric vehicles. And we have seen that they have started to make a real impact over the last few years. We also need, if we are building up these uses of electricity, because the reason we are talking about electrifying is that we have seen that it is easier to decarbonize electricity supply than it is to decarbonize other elements of our energy use. So if we use more electricity, we need to generate more electricity. And that means, certainly in the part of Europe where I'm based, using more wind energy, using as much solar energy as we can get our hands on. Thankfully, the sun is shining in Ireland today, but it doesn't always happen like this. So we need more growth of renewables, and we need it faster than we've ever done it before. And then this is maybe an issue that's specific to certain countries, is certainly specific to Ireland. We need to cast our sights offshore. We need to look at what lies beyond the horizon in our oceans and look at truly exploiting the renewable resources that are out there. Ireland has the potential to produce 10 times more electricity than it consumes if we exploited the full extent of our offshore wind energy resources. So these are some of the approaches that are currently being used in Europe to try and get ourselves off fossil fuels and to try and reduce our greenhouse gas emissions. But what's left? What about vehicles that have to drive very long distances, that have to haul very heavy loads? What about industrial processes that have to achieve extremely high temperatures? What about commodities that we need for everyday life, like fertilizers, like plastics? How do we make these in a zero carbon world? And then how also do we look at these transportation systems that have to span the globe, that have to move goods around the world in container ships, move people around the world on aircraft? How can we think about decarbonizing these? It's going to be, it's not going to be possible to electrify absolutely everything. So what else can we look at? But before we get to what else we can look at, what new challenges are there as we start to move towards a more renewable energy system? How does that present challenges for how our electricity system works? This is just a simple representation, again, using Irish data, of electricity demand in the black, which is usually pretty constant, and wind energy generation in the red. And the difference between those two until now has been made up with fossil fuels. So at times when we produce small amounts of wind energy, we have to switch on our fossil fuel generators. If we imagine a world with lots of renewable energy, the peaks will be higher, but the troughs might not be much higher. So how can we fill those gaps? And just to give a quick graphical representation, this is the largest pumped hydro energy storage plant in Ireland, represented to scale. That area represents the amount of energy stored by that plant. So you can see that for that period of 15 days where we had very low wind production in Ireland, the energy storage in that large-scale pumped hydro plant is quite small. And this maybe will focus minds even more. This is the largest battery storage plant in Europe, which was built in Ireland a couple of years ago. And it is an even smaller amount. So while batteries are extremely important in balancing instantaneous supply and demand on the grid, they are not very large energy storage sites. So how can we address these problems that are going to come online as we move to a zero carbon energy system? Well, green hydrogen is potentially a missing link to this. Green hydrogen involves the use of renewable electricity to split water in a device called an electrolyzer, to transport that hydrogen to where it's needed, either through pipes or through ships or through trucks. And the fact that we have a chemical means of energy means that we can store that energy from times when we have the renewables to times when we don't. Because the thing with energy demand is that we generally have no say in when energy gets used. Energy is used when it's needed. Now, that can be controlled to some extent by demand management, but it can't always be. So once hydrogen is produced and stored, it can be used across a number of different sectors to decarbonize. So we've done some work over the last few years about trying to quantify this, and we've again been coming at this from an Irish perspective. And the results of this are comparable to other countries, but maybe not directly so. So we envision that by 2050, about 8% of the electricity generated in Ireland could be generated by hydrogen being burned in gas turbine engines, the same type of gas turbine engines that are used to generate power right now from natural gas. About 12% of heating could come from hydrogen in Ireland. And in transport, there's a mix of different transportation options here. We are projecting very small use of hydrogen in private cars, but larger use of hydrogen in, again, these heavier, these harder to decarbonize sectors such as shipping, trucks, and heavy duty public transport. We also have started looking at how hydrogen can fit into our electricity sector. So again, we're returning to our pumped hydro storage site represented in blue and our battery storage site represented in yellow. Ireland and the Northern Irish government are jointly starting to investigate whether hydrogen could be stored in a cavern, in a geological salt cavern structure in Northern Ireland that could store energy for the entire island of Ireland. And the minimum estimate of how much energy could be stored in that cavern is shown by this blue box here. So it's orders of magnitude larger than the type. Oh, sorry, my captions are missing. It's orders of magnitude larger than the amount of energy that is currently stored in our pumped hydro plant or in our large-scale battery storage plants. So there is a huge potential storage resource out there for hydrogen in geological settings. One of the issues with hydrogen is that we currently don't use hydrogen much as an energy resource. It's used in certain industries, but we are now starting to see that those of us working in hydrogen are having to consider both the supply and demand of hydrogen together, bringing these on stream together. And how this is being currently promoted is through the use of hydrogen hubs or hydrogen valleys. So this represents some work that we've been doing with the Irish government and the Northern Irish government on linking up potential areas of supply of hydrogen, for example, where we have large-scale renewable resources, so these are mostly at coasts, and where we could potentially be using hydrogen. So the industry in Ireland, cement production and power generation. We're also looking at how Ireland can get connected in to be an exporter of hydrogen to Europe. And one of the routes that could be availed of is the European Hydrogen Backbone, which is a pan-European project to convert the current natural gas pipe network into 100% hydrogen piping networks. And this would not be to deliver hydrogen into people's homes. This would be for moving large-scale amounts of hydrogen from areas of production, where the renewables are, to areas of demand, where we have the heavy industries. So with a network like this, we would envision hydrogen being produced by wind in Northern Europe, being produced by solar in Southern Europe, and being moved by pipelines to the central hub, the industrial heart of Europe. And what I want to sort of finish this presentation on is to say that we are aiming to do that right here in Galway, in the west coast of Ireland. We have received funding from the European Commission to build what's called a hydrogen valley. So we're aiming to produce hydrogen at a wind farm here in Ireland and use that to power hydrogen-powered intercity buses and hydrogen-powered trucks, and eventually to power boats and small aircraft that serve the islands off the west coast of Ireland. So this project started just this month, and we'll be running it for 5 years, and we hope to keep you all updated with how this project goes as we start to try and decarbonize these really hard to decarbonize parts of the Irish economy. So I'll leave you with the summary on the page, and I hope I didn't go too much over time. And I'm happy to take any questions later on. So thank you very much.
It's a big thank you to Rory for this very insightful presentation. I'm sure there will be questions for the discussion round. We can truly appreciate your expertise in this topic. And I think now we can move on to our final speaker today, Ana Picayo Perez, with a talk on the future of energy in building for thermal comfort. Anna is currently an assistant professor of the University of the Basque Country, north of Spain, and a researcher at the Consolidated ENLIGHT group. She received her PhD in energy efficiency and sustainability and engineering and architecture area in 2019. Her research areas are related to testing, analysis, and optimization of building energy supply systems, thermoeconomics, and diagnosis application in buildings. Likewise, according to those areas, she made more than 15 publications in JCR journals, a book titled Exergy Analysis and Thermoeconomics of Buildings, Design and Analysis for Sustainable Energy Systems. She also participated in various book chapters and contributed to more than 30 international and national congresses since 2015. It is my pleasure to welcome Anna here with your talk, and the floor is now yours.
Thank you very much, Anna. Okay, I think that is it okay? Everybody sees the...
Yes.
Okay, thank you. Okay, so that's the last presentation. As Anna told us, I'm Anna Picayo-Pérez from University of the Basque Country, and I came here to present the presentation called Future of Energy in Buildings for Thermal Comfort. Before starting the presentation, I want to say that pictures are obtained from eStock platform, and since the title of the whole session is Future of Energy, I want to start the presentation saying that without energy and its transformations, there would be no life. That's why everybody needs energy. All the human beings and the animals need energy to be alive. We are always speaking about energy, but energy has different forms. The energy that we use is called final energy. And as Rory already says, in the Sankey diagram he showed us, the three main consumers are buildings, transportation, and industry. And all that final energy that we use in buildings, transportation, or industry comes from a primary energy obtained from natural resources that can be divided in renewable or non-renewable resources. And in between primary energy and final energy, we have power plants, so transformation plants, which take the primary energy and convert them in the final energy in the way we use. So it's very important to define a difference in between the demand that we need for our use and the consumption of natural and primary energy. And in between both of them, what we have is the efficiency of the energy transformation itself. And what should we do? As Rory already says, the idea is to decrease the consumption of the natural resources in order to decrease the non-renewable resources consumption, because the depletion is something common known, and everybody knows that we need to decrease that consumption in order to contribute to a zero or neutral CO2 emission world and a more balanced world. According to that, in order to reduce consumption, we need to reduce our demand, our habits, our energy consumption profiles. But many times the demand cannot be decreased at all, and instead we are increasing it. So once we decrease as much as possible the demand, the other way in order to decrease the consumption is to improve the efficiency of the energy transformations. This slide only shows which was the percentage of distribution in Spain by 2020, according to the energy mix of that moment. As we see, almost the 1/3 was related to nuclear power, and then it was wind or solar and hydraulics renewable energies in order to to create the electricity in that moment. But according to the demand, the Spanish demand in 2019, in this case, was, as I already told, the main consumers were the industry, the transports, and homes and services. This picture is similar in Europe. As in Spain, the city's finally energy requirement, which means homes or buildings and tertiary sector, is almost 1/3 part. In Europe, it accounts for the 40% of the total energy consumption. Therefore, we need to download this kind of demands. According to buildings itself, which are the energy demands? It's common known that we have heating demand and electricity demand. Heating demand, we have heating requirements in winter time and refrigeration in summertime. More now where the global warming is so high. And we also have energy demands for ventilation. And ventilation is an energy demand that requires a lot of energy quantity since we throw the already acclimatized indoor air to the outside and we take clean air from outside. We need what we need to pay for again for acclimatize, but it's very important more now that we have already lived a COVID-19 pandemic. And the last main demand in buildings is domestic hot water for sanitary demands for kitchen and toilets. And the electricity demands covers the requirements for electrical devices or lighting. As I already said, this demand is covered by the consumption of primary energy. But however, that demand is supplied by the terminals. They can be heaters or radiant floor, taps for water, or valves, or another kind of terminals for electrical devices. And the energy in order to supply the demand in those terminals comes from engines, from the technology called generators. And it's important to know that the bill we are paying for is for the energy you use to supply the generators. Therefore, we have two different efficiency. The one is the total efficiency of the energy change from the consumption to the demand, from the primary energy to the use at homes. But we also have the efficiency of the engines itself, and those kind of efficiencies are required to be as higher as possible. It's important to say that more than 65% of primary energy is lost in the conversion of useful energy, as Rory again says in the Sankey diagram he showed us. Speaking about technologies, I think that everybody is familiar with this kind of label. This is the energy level which any engine needs to have if they are consuming energy. It's an intuitive level. What they say is that if you have an engine that consumes the average energy that that kind of engine consumes, for example, a fridge, it will have a D level. If they consume 40% less than the average one, it will be an A+, and if it consumes more than the average one, it will be, for example, an F. So the idea is to have the most effective technology as possible, but it's also very important to use renewable resources in order to supply that energy to those kind of engines. As Luka also showed us with heat pumps supplied by geothermal heat. This is a picture that is taken or adapted from ISO standard 52001, which explains how we can calculate all the transformations along the energy chains from the primary energy to the demand at homes I will not enter in detail in this picture, but if somebody needs help with this, you can ask after in the questions. But the idea is to calculate how much primary energy we need to cover our demand and to decrease it as much as possible. Continuing with buildings and the future of buildings, future of energy in buildings, well, the present of energy in buildings. All the state members of the European Union have already defined a nearly zero energy building. According to a Spanish regulation, a nearly zero energy building is a building that almost do not consume energy and has an A level, since the emissions and the energy consumption are very low. Nevertheless, the idea for the coming buildings is to build net zero energy buildings, which means that they are buildings that they do not consume any kind of energy, since they produce themselves and locally the demands they have inside. In such case, when the production and the consumption are equal, that building itself do not consume anything. But the promising future is to create the positive energy buildings, which are kind of little power plants that they can create and produce more energy than the demand they have themselves. For example, by including micro wind technologies or photovoltaics or solar collectors or geothermal energy. So including their renewable energy in order to produce more than they consume. As an example, I will explain briefly which is a passive house standard. Maybe some people are familiar with that, but it has 6 different rules, let's say. It's a house, well, there are many kind of standards, but this is a passive house standard. It's a building that has a very high insulation, proper insulation, in order to decrease the heating and refrigeration demand as much as possible. It's very compact building in order not to control leakages or losses. There are no thermal breaches. Thermal breaches are like highways for heat losses. So if you avoid thermal breaches, you don't have those kind of losses to the outside. Therefore, with the first, second, and third step, we can have a building without heating and refrigeration demands. We also have proper windows, for example, with 3 glass windows, in order to have as much as higher sun radiation income, but not losses to the outside, and proper orientation. It also includes a heating recovery ventilation in order to recover the energy of the extracting air from the inside. When we have these 6 points in our house, we can arrive to decrease our energy demand by 90% comparing to the traditional homes. So the rest of energy can be supplied by renewable energies in order to compensate the demand. And also with internal gains inside the house, or the solar gains, we can even compensate all the heating requirements. These types of buildings are buildings from the present and buildings for the future, but what we need to do, as Rory says, it's to decrease our demand itself and try to make the future of energy a little bit more positive. Thank you very much for your attention. If anybody has any question, do not hesitate for asking that. Okay. I think it's okay. Yes.
Great. Thank you very much, Anna, for your talk. So this concludes our presentations on the future of energy. And at this point, I want to thank our speakers for their very insightful talks. You have surely covered a lot of ground in your presentations, and now we can dive into a discussion. And I'm happy to open the floor to questions. So we can first have a look at the chat. We already have one question for you, Anna. What challenges and opportunities do you foresee in implementing and promoting net zero energy buildings on a larger scale?
Okay, yes, thank you, Claudia, for your question. Okay, I didn't have many times to speak in my 10 minutes talks, but another, I don't know if I'm answering your question itself, but nowadays we are working in a project inside the Basque Country which is related with energy communities. And energy communities are like communities of buildings which are working together in order to create their own local energy and to supply the demand by the local resources. We are working with photovoltaic, and we promote I don't know how to say, we try to cover the energy demands of the communities in the building itself. They are not net zero energy buildings, but we are trying to increase the energy level, and also, as Rory says first, also to electrify their demands. Since if you put, for example, a heat pump that is supplied by electricity, and that electricity can come from your roof, you can try to achieve your net zero energy building faster. I don't know if I'm answering your question or not, but and the opportunities is the electrification with heat pumps in Spain. In the Spanish government is suggesting us to use heat pumps all the time and renewable energy with photovoltaics, but there are more things than that.
Thank you very much for your response. We can see if there are any follow-up questions on that, or this is also a good point to remind you that we also have a brief networking event after this lecture, so you can also use that for a discussion. Before any other questions come up, let me jump back to the first talk of our today's lecture, to Luka. And I have a question on the temperature of the groundwater. Perhaps you could elaborate on any detriments to the environment when changing the temperature of the groundwater?
Yes, thank you for the question. Of course, with an ETA system, you change the temperature of the groundwater. And if you change the temperature of the groundwater, this could cause some mineral precipitation or some changes in the the biological activity, and this can be detrimental to the environment, but also to the efficiency of the ETA system itself. Because if you have precipitation or if you have biological growth, clog your pores or clog your filters, and then you decrease the capacity of your system. But for the environment, on the long term, the effect is still poorly known. So it's very important in the future to keep monitoring these changes, because the temperature change is only relatively small. It's about 5 degrees Celsius in change. And when you stop the operation of an ETA system, the temperature distribution in the subsurface goes back to normal again. So the long-term changes and the long-term effects are still poorly unknown, but it's important to watch out for the detrimental effects.
Yeah, thank you very much. There is a follow-up question from a fellow speaker to Luka. Can be an ATES an option in building energy system rehabilitation?
I'm not sure what you mean by energy system rehabilitation. If you could explain.
Anna, would you like to elaborate?
Okay,
on
I was
that?
writing in the chat, sorry. No, I mean that many times what we do with, I'm taking a little bit of topic, to my topic, I'm moving to my topic, but when we want to decrease the energy demands of buildings, we rehabilitate them, we rehabilitate them, the envelope and everything, and then we rehabilitate the energy systems. For example, we change boilers and we change them with renewable energy. So, I mean, can you, from an already existing building, incorporate an ATES there, a heat pump that is supplied by an ATES, or is it not possible? I don't know.
Yeah, you can implement an ATES system in a rehabilitated building if it's well insulated, of course, because otherwise it's always a waste of energy. But if you spend a lot of money on an ATES system, you should be sure that you have a well insulated building. Most of the time, ATES is done for newly constructed large buildings, but it can, of course, if you have thorough renovation of an older building, you can incorporate ATES as well.
Thank you, Luka, for your insights on that. There is one question for Lei. How to solve the problem of huge computational demand in deep geometrical models?
Well,
Hope we have a couple of minutes to to discuss that.
Yeah, I'll try to make a short answer on it. It's quite a great question about the modeling problem, especially for the large scales modeling. For each modeling, it will cost like sometimes it depends on the complexity of model. Sometimes if you are running a lot of model like hundreds or thousands, it would be really time cost. So in our research, we are based on the data set. We are now using some machine learning method to predict the model's responses with the parameters relationship. It'll be a great option to evaluate the truly responses by the data you have, and it don't need to run a lot of models in any software. You just got the data, and the machine learning model will tell you what the response is. It's quite a complicated model, but it will really faster the calculation. So yeah, that would be a nice choice to avoid the large scale and the time cost numerical modeling. Yeah.
Thank you very much for your input. We have some more questions in the chat.
How much power can be generated? It should be, I've been in the first figure, I'm looking for my first figure on my sliders. The high temperature, especially very deep high temperature, is like more than 100 centigrade. So it's also hot water is some steam. You can like exact zero, so it can use to generate electricity. But however, I'm not really focused on the power, how much power or how many energy it can extract from there. My research really focused on the rock mechanics, focus on the risk assessment, the stability things. So maybe I can I can check it later, but I'm not really know it very exactly.
Thank you very much for your response. Unless there are some follow-up questions on that, I'd like to move to one more brief question to Rory. With the focus on hydrogen deployment at the hubs and valleys, can you or do you foresee challenges related to infrastructure development and scalability? Could you perhaps comment on that?
Sure. Yeah. Thank you for the question, Anna. There are huge challenges with infrastructure and hydrogen. Because we are bringing on essentially a new carrier for energy, it's not really the case that we can just, use existing infrastructure. There are some studies underway to see how much hydrogen can be added to the natural gas pipe network. And the answer is it depends. A lot of the newer pipes are quite suitable for hydrogen, but a lot of those newer pipes bring gas into people's homes. And but this is probably not a very cost-effective way to use hydrogen. Heat pumps, the work that people are displaying here on electrification of heat and use of geothermal energy will probably be much cheaper for decarbonizing people's homes. So what we really need to think of is, how can we move large quantities of hydrogen from supply to demand? This will probably mean building new pipes. But, so this will be an expensive undertaking, but the technology exists. There are thousands of kilometers of pure hydrogen pipes around the world. They just need to be built in the places where we have renewables and where we have energy demand. But it's not. We're not solving a new scientific problem here. It's a question of, is there the will to fund this?
It's a very good answer. Thank you very much.
Thanks.
Before we wrap up, does anyone have any final thoughts, questions, or comments to share? Well, if not, this concludes our session on the future of energy, and I'd like to thank all of our speakers for your contributions.
Yes, sorry. I want to thank also Rory for his presentation, yes. And I would like to see your project when it's finished. Because it's a very huge project. So congratulations.
Thank you, Anna. That's very kind of you. I hope so too. I hope it works too.
Yeah, thank you. Yes, thank you again to all of the speakers for your contributions today. You made this lecture very valuable, and I hope that's what our viewers think as well. And I also thank all of you for the questions. And at this point, we can move on to our networking event on Zoom. So everyone who's registered for that has also received a link. And if you're part of it, then see you there in a bit. Thank you very much. And to everyone leaving right now, goodbye.
Thanks, everyone.
Bye-bye.
Bye-bye.
Thank you.